Welcome back to the week 8 of the problem solving session for the course Thermodynamics. And in this week, we will be primarily dealing with the second law of thermodynamics, or basically speaking, the introduction to the second law of thermodynamics. So, if you recall, from the first law of thermodynamics, that was basically given by delta Q is equal to dE plus delta W. So it's a way to understand the law of thermodynamics that from the first law of thermodynamics, the thermodynamic property that came into picture was the internal energy, or the energy of the system, given by this. And primarily, if we consider that the kinetic energy and the potential energy in the system are considerably low compared to the internal energy, so this is basically equal to du. So internal energy was introduced in the first law of thermodynamics. Similarly, in the second law of thermodynamics, we will again be introduced to a new thermodynamic property, that is the entropy. And right now, at least in this week's session, we are still not be discussing about entropy, but we will basically be discussing the elements that are necessary to understand the term entropy itself. So with that motivation, let us start today's session. So as per our regular agenda, I will briefly go through the discussions that Professor Anand had taken in the lectures, and if you have any doubt, you can stop me at that point, and then we will discuss some problems related to this week's discussion that will help you to solve the assignment problems for this week. Okay, so we briefly go through the first law of thermodynamics just as a recapitulation to understand what first law of thermodynamics is and what are its conclusion, or what are the conclusions that we can obtain from the first law of thermodynamics. From the first law of thermodynamics for heat exchangers, we get that it's just a recapitulation. Okay, that we get that for heat exchangers we have the summation of mi dot hi is equal to summation of m dot e he. Okay, so this was the conclusion from the first law of thermodynamics for the heat exchanger. Basically, the first law of thermodynamics for a steady flow process, or popularly known as the steady flow energy equation. Similarly, in the case of nozzles and diffusers, we got that hi, the steady flow energy equation reduced to hi plus vi square by 2 is equal to he plus ve square by 2, where vi and ve are the inlet and the exit velocities. Now, if we consider the first law for an insulated constant volume process, we will have that the net heat interaction is 0 because the system is insulated. And similarly, if the system is for a constant undergoes a constant volume process, then the change in volume is 0, so the net PdV work is 0, so the net work interaction is 0 as well. So from that we get that dE by dt is equal to 0, which basically means the energy remains constant. Or if we consider the kinetic and potential energies to be negligible, then we can say that internal energy remains constant, it is U1 equal to U2. Now similarly, if we consider an insulated constant pressure process, we will have that Q is equal to 0 because the system is insulated, so there is no heat interaction. And similarly, since now the system can undergo a volume change because the process implies that it is a constant pressure process, so there will be some work interaction. Now if we combine the change in internal energy to the change in work done, then we can basically combine the U1 plus PV terms, then we'll get that the net enthalpy of the system remains constant. Okay, so from the first law, these are the conclusions that we get. We get the relationship between the heat and work, and we basically see that, as I already mentioned, the relationship between heat and work, that is, write it again, delta Q is equal to dE plus delta W. So this is the relationship between the heat and work. Or for a cyclic process, we get that the cyclic integral of the net heat interaction is equal to cyclic integral of the net work interaction. So this is the relationship between the heat and work interaction that we get from the first law of thermodynamics. Moreover, we are also introduced to a new thermodynamic property, that is the energy of the system, or the internal energy of the system, if the kinetic and the potential energies are negligible. Now, but the thing is that we do not actually know about actual conversion, like how the energy is being converted. And moreover, the more important thing that we do not know from the first law of thermodynamics is that whether the given process is feasible or not. So if you consider an example, it is for example, the transfer of heat from a hot system to a cold system. So we know that the temperature gradient is always from a region of higher temperature to a region of lower temperature. So if say a hot cup of coffee is being left in the atmosphere, that is at a lower temperature than the cup of coffee, then since the temperature gradient is from a higher temperature to lower temperature region, then understandably the coffee will cool down and reach the temperature of the atmosphere, right? So there is a temperature heat flux from a hot region to a cold region. Okay, so this is a spontaneous process. Okay, the uh, the hotter object will get cooled down if left in a surrounding that has a lower temperature compared to it. And similarly, if we keep a lower temperature body, for example a ice cream in the atmosphere that has a temperature lower than the ambient temperature, then the temperature of the ice cream will increase, right? Again, the heat from the surrounding will go to the ice cream, that is, then it will heat it up, so the temperature of the ice cream becomes equal to the ambient temperature of the surrounding. So this is the spontaneous direction of heat transfer. It is from a hot region to cold region. But we we also observed some similar phenomenon where a temperature from a cold region to hot region is where there is heat flux from a lower temperature region to higher temperature region. For example, in the case of refrigerator, we need to cool the temperature of the system within the refrigerator to keep all the food items in the refrigerator to be in a cooler temperature, so that it is preserved, right? So in that case, what we do is we take out the heat from the already cool region within the refrigerator and expel it to the atmosphere. So there are scenarios where we can observe heat transfer from a colder region to a hotter region. But the important thing to recall is that this process is not spontaneous. So it will not occur spontaneously. What happens is that we need to apply some additional external work to the system so that we can achieve this heat transfer from a colder region to a hotter region. Okay. So the thing is that the first law of thermodynamics, even if it is valid for a spontaneous process, that's well and good, but it's again valid for a non-spontaneous process as well. So the directionality of heat transfer or work interaction is not taken into consideration in the first law. So the first law is not capable enough to understand this spontaneous nature of the heat flow, which is, I guess, one of the very crucial elements of to understand while we are reading or understanding thermodynamics. Okay, so these are the limitations of the first law of thermodynamics. Now that's why, to overcome these limitations, the scientists or researchers work upon to understand another phenomenon, that is the entropy. Okay, the entropy, and that we will not discuss about in today's session. We will discuss it about in the next session and the subsequent session, in the remaining sessions, and you will understand that this property of entropy plays a crucial role in understanding this spontaneous nature of heat transfer or heat interaction or work interactions. Like how does a spontaneous how to classify a spontaneous and non-spontaneous process. Okay, so we will get a hand will know more about it when we discuss about it thoroughly in the next sessions. Okay, but still this session is important because we will get to know why the term entropy comes into picture while discussing the second law of thermodynamics. Okay, so let us take an example. For example, in the case of a Joule's experiment, as this was discussed by Professor Anand in the lectures, we see that as the in the case of a Joule's experiment, both the heat and work interaction are negative. Why? Because if the weight goes down, then it rotates the propeller within the system that does work on the system. So if work is done on the system, then by our general sign convention we have that work interaction is negative. Again, if we consider that because of this work interaction, heat is being generated within the system that is being expelled out of the system from the boundaries, then heat coming out of the system would imply Q to be negative. Okay. Now we get introduced to the term of to a direct heat engine in the case where the heat transfer is positive as well as the work interaction is positive. That basically means that it will mean that we transfer heat to the system. That's why the sign convention is positive, and the system then, after it inheriting this heat transfer from a thermal reservoir or some external source, the system does some work. And this kind of systems which does work after inheriting or absorbing heat from the external surroundings, uh, then such kind of engines are known as direct heat engines. Okay, so Deve, do you have any doubt? So you raise the hand. You can either ask or just write in the chat. Right. Any doubt? Oh, okay. So thing is, we will. Can you write that question? Meanwhile, I will continue to discuss the topics. Then, after I read the question, then maybe we will be able to discuss about it. But primarily, like our regular agenda is that we will discuss the topics in the class that was discussed in the lectures by Professor Anand. Then they will solve some problems that are similar to the questions that we have in the assignments. I'll ask you to solve the questions, and then if you have any doubt, then we can discuss about it. But still, you can write the question. That's fine. Okay. I hope it's clear. You can write the question. It's completely fine. I will. Meanwhile, I will just continue to take the session. Okay. Okay. Yeah. So that's the direct heat engine. That the system absorbs some heat from a thermal reservoir or some external source, and then and by absorbing this heat, it does some work, and thus the sign convention for both a heat and work interaction is positive. Now, as I already mentioned about refrigerator, where we absorb heat from, where we transfer heat from a colder region to a hotter region, in that case, to achieve such kind of non-spontaneous phenomenon, we need to take the help of a reverse heat engine. Okay, and such kind of reverse heat engines are primarily known as heat pumps or refrigerators, and we will get to know about the difference when we discuss the following when we discuss it thoroughly in the next page. Okay. Or so now this the example for direct heat engine, that is the system absorbs heat. Okay, steam table provided the internal energy saturated. Okay, so the thing is, we have already taken this question, I guess this exact question in the previous week's session. So the lecture video as well as the problem solving session video is already uploaded in the website, so you can kindly check it. Okay, so, moreover, the question is not complete, so I'm not able to help out. So it would be better. Okay, so saturated liquid at 4.6 degrees Celsius. Okay, so it's quite simple. Let me just give you some hints. Oh, interpolation. You want to know? Oh, yeah. Thank you. He's answering. Yeah, you need to do interpolation. So we'll see in the, if you go into the steam table for a temperature, like where the steam table is given in terms of temperature, you'll see that there is temperatures. The thermodynamic properties are given for two different temperatures. I guess for, if I'm not wrong, let me just go to the steam table. It is given for just wait a minute. It is given for 0.01 degrees Celsius and 5 degrees Celsius. And since your given temperature is in between 0.01 and 5 degrees Celsius, you need to do some linear interpolation. Okay. So how to do linear interpolation, I guess Professor Anand has extensively discussed in the lectures. Moreover, I have also solved the same problem in the problem solving session of last week. So I kindly request you to go to that lecture video, do the linear interpolation, and you will easily find the value of the internal energy of the saturated liquid, basically you need to find UF, right? So I hope that helps you out. More Anil Patil sir has also given the solution or key to this question, so you can refer to that. Okay, so I guess we can proceed further. Thank you. I hope that helps you out, Deve. Please let me know. Okay, so we discussed an example for a direct heat engine. So this direct heat engine is the basis of or many is the base for the working of many power plants, basically the thermal power plants or nuclear power plants, where which primarily is the source of electricity for the is the source of electricity for our country. Like most of the electricity is being produced by these thermal power plants or the nuclear power plants as well now, and so that's why, since it plays a crucial role in the energy production for our country, we need to know about its working, right? And this works on the base on the on the basis of a direct heat engine. Okay, direct heat engine, or you can also, some books refer it to as heat engine itself. Okay, so direct term is sometimes omitted, so direct heat engine or heat engine, so these terms can be used interchangeably, so direct is not necessary. So it's just to show you that how it is different from reverse heat engine. Okay, so in the case of a direct heat engine, or we take the example of a power plant, and this power plant primarily works upon the basis of the Rankine cycle. It's based on the Rankine cycle, and we will discuss about Rankine cycle in the last two sessions of this course. Okay, when we are introduced with the term with the property of entropy, we'll discuss the TS diagrams, the temperature entropy diagrams, and then we'll discuss about the Rankine cycle. Okay, so but for now you can consider it as a heat engine or a direct heat engine. Okay, so in the case of a power plant, what happens is that the water being heated in a boiler, so since the water is being heated in a boiler, it will absorb heat from the surroundings, so QH is being given into the system. The system is denoted by this blue dotted line. Then this hot water is being expanded in a steam turbine. Okay, this hot water, the steam generated from the boiler is being used to rotate the steam used to rotate the turbine, which in turn rotates the electric generator to form electricity. Okay, and this steam, after being expanded in a turbine, now goes to a condenser where it is condensed to back to a liquid form. Okay, since it is being condensed, it rejects heat to the atmosphere, so Q is being emitted out of the system. It is denoted by QL. QL primarily here, QL and L and H denotes the higher temperature and the lower temperature. So since a higher amount of heat is being given to the boiler at a higher temperature, so it is denoted as QH. Similarly, the condenser rejects heat at a lower temperature, so it is denoted as QL. Okay, and then this condensed liquid is then again given back to a water pump, which pumps it back to the boiler where it is again being heated, and this cycle continues. Okay, so we'll see that there are two heat interactions and two work interactions. Okay, so one heat interaction is between the boiler and the system, and the second heat interaction is between the condenser and the surrounding. Okay, so there are two heat interactions, and two work interactions are the work produced by the turbine, and second is the work being given in work input in the water pump. Okay, so I should actually denote it, because here I have used the W net to show the net work done, but actually there should be a work done from the turbine and work input to the pump. Okay, so these heat engines can be also be denoted as from in the form of a schematic diagram as shown here. So it's a very extensive diagram, so we can simplify it in the form of a simple schematic, where we again see the boiler is being denoted here, where we denote the heat interaction to the boiler as Q1, heat input to the boiler as Q1, then the steam is expands within the turbine, then generates some work WT. Similarly, now this expanded steam is put back inside a condenser where it is being condensed into the liquid form, and this condensation results in the releasing of a heat Q2 from the condenser, and this condensed liquid is then pumped back, is transferred to a water pump, which pumps back this water into the boiler again. Okay, and this cycle continues. And since we need to apply some work to pump this liquid from the condenser to the boiler, so there is some work input into the system. Okay, or in a very simplified fashion, you can denote this direct heat engine in this form, like the thermal energy reservoir T1, from the thermal energy reservoir T1, which is at a higher temperature. So let me just, yes, it is shown here, T1 is greater than T2. There is a heat interaction of Q1 with your heat engine, so the entire heat engine is being reduced to this small circular pattern given denoted here, that is E, and this heat engine then produces a net work W, which is basically Wt minus Wp, the net work produced in the turbine minus the net work input to the pump. And usually the net work produced from the turbine is much higher than the net work input to the pump. Okay. Similarly, now we can indicate or denote a reversed heat engine. Okay, so reverse heat engine, so it basically implies heat pump. So I will show you one crucial thing regarding this. So in the case of a reverse heat engine or heat pump or a refrigerator, what happens is that, say I am taking the example of a refrigerator. So what happens is that now the evaporator, in the evaporator we absorb the heat from the system where from the surrounding. Basically in this case the surrounding would be the food which we want to keep cool. Okay, so the heat from the food items within the refrigerator is being absorbed in the evaporator, where the evaporator is then being takes up the heat Q2 and then transfers that hot liquid into the compressor, right? Not that hot, but comparatively little hotter liquid compared to the evaporator, because it takes up the heat, so it gets heated up. Then this evaporator is being transferred to a compressor, where we input a work WC or work done in the compressor, which compresses this this evaporator into in a much denser form, in the form of liquid, and this liquid is then transferred back to a condenser where, sorry, I'm extremely sorry, this evaporator is compressed in the compressor. Then again, since the density or the specific volume of the evaporator reduces considerably in the compressor, but still it may have some some elements of it may still be in the vapor form. And in order to ensure that it is completely in the liquid form, so that the expansion device can is devoid of any liquid, vapor form, so it is being condensed in the condenser, where the heat is being rejected out of the condenser, and finally this condensed liquid is then expanded in an expansion device, where this expanded form of the evaporator, which finally result in the temperature of the evaporator or the refrigerant to be much lesser than is comparatively lesser than the food within the refrigerator. Why? Because since we want the heat transfer to occur between the refrigerator in the evaporator and the food, so we need the refrigerator to have a lower temperature compared to the food. That's why the expansion device does is that it lowers the temperature of the refrigerator even further, so that the temperature of the refrigerator is lesser than the food within the refrigerator. That's so that there can be some heat transfer. As we know that heat transfer occurs from higher temperature lower temperature, so the the food being at high temperature transfers its heat to the refrigerant, which is at lower temperature compared to the food. Okay, and you will see that in this cycle, you can see the direction of this cycle. Okay, so in the case of a right heat engine, all this process occur in a clockwise process, and that's why we denote it as a clockwise arrow in the heat engine. Similarly, this process occurs in a reverse cycle, occurs in an anti-clockwise fashion, and that's why we, in the schematic diagram or the simplified diagram of this refrigerator, we denote it as an anti-clockwise arrow in the heat pump or the refrigerator. Okay, in this case I've discussed about the refrigerator. Similar can be discussed about heat pump, where this is our heat interaction of interest. Okay, basically what happens is that in the case of heat pump, heat is being absorbed from the colder surrounding and being pumped back into the room where we want to keep it hot. Okay, so this temperature will be higher than the ambient temperature within the room, so that the room can be heated up, and the additional heat that is used to heat up the room is being absorbed from the colder surrounding outside the room or the system. Okay, so that's the main difference. In the case of heat engine, we denote it as a simple E and a clockwise direction arrow, and in the case of reverse heat engine, we denote it as a reversed E and in a arrow in the anti-clockwise fashion. Okay, so these are the sign conventions or symbols used to denote distinguish a heat engine or heat pump, heat engine and a heat pump or a refrigerator. Okay, so there is a work output from the heat engine and there is a work input, network input in the refrigerator or the heat pump. Okay, so I hope this was clear, the working principle of a heat pump and a refrigerator and a heat engine as well. So I hope it was clear. Then let us go to the analysis part, like how to analyze such kind of systems. Okay, so the two main key terminologies involved in the analysis of heat engines and heat pumps are the thermal efficiency and the COP or the coefficient of performance. Okay, so in the case of heat engines, we need to deal with the thermal efficiency, and in the case of heat pumps or refrigerators, we deal with the coefficient of performance or COP. Okay, so in the case of heat engines, the thermal efficiency is given by the net work done upon the net heat input. Okay, so you'll see that if I go back to the diagram, let us keep it as such. So the thermal efficiency for a heat engine, which is this one, is given by the net work done, that is W, divided by Q1, that is the net heat input to the system. Okay, so it is not actually Q net, but it's only the net heat input. Okay, so that's very important to recall. Okay, so eta is given by W net by the net heat input. Okay, so that's the thermal efficiency for a heat engine. Now in the case of a heat pump or refrigerator, the important terminology is the coefficient of performance, which is given by, actually if I write it in a generic fashion, so COP will be given by desired effect by the net work or the W net. Okay, so in the case of a heat pump, our desired effect is the heat expelled out of the system that is used to heat up our room or the storage. Okay, we need to heat up a storage or a room, so that's why the heat expelled out of the heat engine or expelled out of the heat pump is of more importance, right? So this is our desired effect. So in the case of heat pump, the desired effect would be Q1, and that's why we write the COP of a heat pump as Q1 by the net work input. Okay, similarly in the case of a refrigerator, the heat absorbed out of a system absorbed out of the system or the area from which we want to cool is a desired effect. So Q2, or basically the heat transfer into the evaporator, is the desired effect. So we will have the COP of refrigerator as Q2 by W net. Okay, so this is the distinguishing factor between the COP of a heat pump and the refrigerator. Okay, these two are basically the same device, but the desired effect are different. So that's why we need to be careful while writing the formula. Okay, so I hope the formula for the thermal efficiency COP is clear, and there's a very interesting relationship between the COP of heat pump and the refrigerator, and which I will tell you eventually. So now let us go to the analysis part. Okay, so the one thing to recall is to keep in mind is that all these devices, the heat engine, the heat pump and the refrigerator, are cyclic devices. Okay, so they undergo a thermodynamic cycle. So that's why we will have that the cyclic integral of the net heat interaction is equal to cyclic integral of work interaction. So you see that even for understanding the second law of thermodynamics, you need to have a strong basis of the first law of thermodynamics. Okay, so that's why for the first law of thermodynamics, for a cyclic process, we have that the cyclic integral of the net heat interaction is equal to cyclic integral of net work interaction, or summation of Q is equal to summation of W. So if we apply it on the heat engine, we will get that Q1 minus Q2. Why minus Q2? So since this is our system and Q1 is a heat input into the system, that's why this will be positive. Similarly, Q2 is heat out of the system, so this would be negative. So our system is this heat engine. Okay, and since net work is coming out of the system, so W will be again positive. Okay, so we have that Q1 minus Q2 is equal to WT minus WP. Let us again go back to just to clarify why WT is positive, because WT is coming out of the system, right? Work is done by the system, so WT is positive, and similarly WP is the work input to the system, so WP is negative. Okay, so just be careful in the sign conventions. That's why I'm mentioning it. Okay, so it will basically give us Q1 minus Q2 is equal to WT minus WP, that is equal to W net. So if you want to find the efficiency, we have eta is equal to W net by the net heat input, it is QH, or the heat transfer at a higher temperature. So we will have W net is again QH minus QL. So it is Q1 is basically QH and Q2 is QL. It's just the matter of sign convention that I use to define the net heat the respective heat interaction. So eta would be QH minus QL by QH. So we divide by QH, you will get eta is equal to 1 minus QL by QH. Okay, so this is the thermal efficiency of a heat engine. Similarly, in the case of a heat pump or refrigerator, you will have minus Q1 plus Q2 is equal to minus WC. Okay, why? Let us go back to the diagram again. So you can clearly see that Q2 is the heat input to the system, so Q2 would be positive. Okay, similarly Q1 is the heat out of the system, so Q1 would be negative. Similarly, WC is the work into the system, so this would be negative. Sorry, this would be negative, and W is the work out of the system or work done by the system, so this would be positive. Okay, and similar to in similar line with the work interactions between the turbines and the pump. Similarly, the work done or work out of the expansion device is much more lesser than the work input to the compressor. Okay, so we will eventually see that in many approximations we only consider the net W net as equal to WT and W input as network input into the so the network interaction within in the heat pump or the compressors as WC, because W is usually much more lesser than WC. Okay, so we have that for the heat pump we have minus Q1 plus Q2 is equal to WC. Yeah, here itself you can see that we have just disregarded WE because W is usually much more lesser than WC. Okay, it's just an approximation used to analyze the systems. So I hope the sign convention is clear now. WC is work into the system, that's why it is negative. Q1 is heat into the system, out of the system, that's why it is negative, and Q2 is heat into the system, that's why it is positive. Okay, so keeping in mind the sign conventions, we'll have that Q1 minus Q2 is equal to WC. Okay, so the COP of a heat pump is again the desired effect by the network interaction. So the desired effect is QS, because in the case of heat pump it is the higher temperature interactions within the system and the surroundings that is of more importance. So it is the desired effect is QH now, divided by W net is QH minus QL. Basically you can take Q1 as QH and Q2 as QL, so we will have that W net as QH minus QL. So COP HP is QH by QH minus QL. You can simplify it even further, but it's not necessary. I will keep it in up to this only. You can simplify it by putting QH in the denominator and then do the respective simplifications, but that's fine. Similarly, in the case of a refrigerator, you will have that the desired effect is the heat interactions at the lower temperatures. It is the absorption of heat from the absolutely date in October. So I'm sorry, I don't know exactly about it. So you can check in the websites. Okay, extremely sorry, I'm not aware of that. I'll let you know in the next class if you attend. I will check it and discuss about it, but right now I do not know. Okay, sorry for that. So in the case of refrigerator, we will have the QL or the heat interaction at lower temperature and our desired effect. So COPR will be QL by W net or QL by QH minus QL. So I hope this were clear. And the interesting relationship between the COP of heat pump and the refrigerator is COP HP is 1 plus COP of the refrigerator. But a crucial thing to know while applying this formula is that both the heat pump and the refrigerator should be operating within the same temperature limits. Okay, basically if such questions are asked where the heat pump is now say you have all the parameters to find the COP of the heat pump. You find it the COP, you find the COP of the heat pump, and but you don't know the heat interaction at the lower temperature. So there are ways to find that, but if you just want to quickly find it, given that the question says that now if we use the heat pump as a refrigerator, what would be its COP? So we're basically saying you that the desired effect has now changed and you're using the heat pump as a refrigerator. So in that case, within the same temperature limits, the COP of the refrigerator would be one less than the COP of the heat pump. Okay, so this is the important relationship between the COP of HP and the COP of R, or COP of the refrigerator. Okay. So now we introduce you to the formal definition of the second law of thermodynamics. So the second law of thermodynamics has two formal definitions in the perspective of from the perspective of thermodynamics. So that is, first is the Kelvin-Planck statement, and second is the Clausius statement. So the Kelvin-Planck statement states that it is impossible for a device operating in a thermodynamic cycle to produce work while having heat interaction with a single reservoir at any T. Okay, so if you recall all the topics that we have discussed till now in this class, you will see that all these devices have heat interactions with two reservoirs. Okay, so just to confirm, let us go back to all the diagrams. So you will see here there are two thermal reservoirs. Let's see, thermal reservoir T1, T2, T1 to T2, two thermal reservoirs. Similarly here, heat interactions between two regions, that is Q1 and Q2. Similarly here, Q1 and Q2. If I go back even further, here also we will see there is heat interaction with two thermal reservoirs, that is QH and QL. So the Kelvin-Planck statement says that it is impossible to have a device operating in a thermodynamic cycle to produce net work while interacting only with a single thermal reservoir at any temperature. Okay, and a device that could produce work while operating with only a single thermal reservoir is known as PMM2, or perpetual motion machine 2. Okay, it is similar to perpetual motion machine 1. We have discussed that a system continuously producing work without any network input. Okay, so this that we discussed when we were discussing the first law of thermodynamics. So similarly, while we are discussing second law of thermodynamics, we again have introduced a perpetual motion machine 2, where a perpetual motion machine 2 would be a device that produces work while interacting only with a single thermal reservoir. Okay, and the conclusion of the Kelvin-Planck statement is that the efficiency of the system of such kind of systems will always be less than 1. Okay, so it's a very important conclusion. Okay, I'll let you know about it when we discuss about the Carnot cycle. Okay, so okay, let me give you a brief introduction about it. So what happens is that when we discuss about efficiency, we usually think that the frictional losses or the irreversibilities in the processes result in the lowering of efficiency. So one might think that if we are able to cancel out all such frictional losses or heat losses in the process, we will be able to achieve a efficiency of 1. But the crucial conclusion, or very important conclusion in the scope of thermodynamics, is that even in an ideal process, okay, even in an ideal process, there is basically a reversible process where there is no frictional losses or reversibilities. Even in that case, the thermal efficiency of such heat engines are always less than 1. It cannot be greater than 1. Okay, it's a very important conclusion. And this conclusion is itself the basis of the second law of thermodynamics. Okay, so let us consider a PMM1 where we can see that the system E is interacting with only some single thermal reservoir which is at a temperature of TH and is getting a heat input of QH, and this heat input is being used to produce a network of W net. So since this is operating in a cycle, so we can write Q equal to W because there is no net change in the internal energy. Okay, so you will have that QH is equal to W net. So the efficiency thermal efficiency can be found out by W net by QH, where W, since W net is equal to QH, you get eta equal to 1. So for PMM1, we will have the efficiency of the system as 1, but we know that this is not a real machine or real system. It's just an imaginary machine or imaginary system. Okay, it will never uh, exist in the real world. Okay, so in the case of real world scenario where a system where heat engine now interacts with two thermal reservoirs, we will have that again from the first law, delta U is QH minus QL minus W net. So this is net heat interaction and not net work interaction. So delta U is again 0 because it is works in a cycle. Then W net is QH minus QL. So eta would be W net by QH, or eta would be QH minus QL by QH, or eta is 1 minus QL by QH. And since QL is non-zero, is not equal to 0, we will have eta always less than 1. Okay, so heat cannot be completely, this implies that heat cannot be completely converted into work even in an ideal cycling process. Okay, it can only be converted into completely into work when we use PMM2, which is again an imaginary machine. Okay, but work can be completely converted into heat. Why? Because I guess in the scope of time we'll eventually discuss that work is a higher grade form of high grade form of energy, and this work can be completely converted into heat, but the vice versa is not possible because heat is a low grade form of energy. Okay. Now the Clausius statement states that it is impossible for any device operating in a thermodynamic cycle to transfer heat from a low temperature region to a high temperature region without the help of work interaction from the surroundings. So now you can understand that the Kelvin-Planck statement is a statement is related to the heat engine, and the Clausius statement is related to the heat pump or refrigerators. So the conclusion from the Clausius statement is that the COP cannot be infinite. Okay, so let us consider a statement, a system that violates the Clausius statement. So in that case, we will have that we are transferring heat from a lower temperature region to a higher temperature region using a heat pump without any work input. Okay, so in that case, we will have that COP of the heat pump, say, is QH by W, and since W is equal to 0, we will have that COP of HP is infinity, which again is not possible. Okay, we will tell you why. Similarly, if we now consider a real world scenario where there is a network input in the system which uses this work transfer heat from a lower temperature region to a higher temperature region, so we will have that COP of HP again would be QH by W. Since W is non-zero, we have COP of HP is QH minus divided by QH minus QL. So COP of HP is has a finite value. So I guess Professor Anand discussed about it in the lectures about the star ratings of refrigerators. So you saw in that lectures, in that thing you saw that the COP are usually within the range of 2.5 to 3.8, right? It's very low actually. So COP being infinite is absolutely impossible, right? So that's why the Clausius statement give the limitation to such kind of systems. Okay, so I hope the Kelvin-Planck statement and the Clausius statement is clear. You will eventually see that how this Kelvin-Planck statement and the Clausius statement is related to the entropy of the system. Okay, or a more generalized form of definition of the second order thermodynamics would be that when we eventually define entropy, we will get to know that the more generalized version of the second order thermodynamics would be that the entropy of the system is the entropy of the universe tends to increase continuously. Okay, so the entropy of the universe can never decrease, so it will tend to increase continuously. Okay, because first law of thermodynamics was the law of conservation of energy, but in the second law of thermodynamics there is no such law of conservation of entropy. So entropy is never conserved, it always goes on increasing. Okay, so this is the generalized statement for the second law of thermodynamics. So I know it may be a bit confusing right now since entropy is not being introduced yet, but this is what you are eventually going to study in the next sessions. Okay, just as a introduction or a highlight, I am mentioning about it. Okay, so there were discussions about the reversible processes and the internal and external reversibilities. So I will just discuss about reversible process. Okay, this is a process that once having taken place can be reversed, and in doing so leave no change in either system or surrounding. Okay, I think the definition is self-explanatory. I'm not going to repeat it. I'm not going to discuss it thoroughly. Okay. If you have any doubt, I guess Professor Anand extensively discussed in the lectures. It will be useful. I'm saving time for the problems that we need to solve. Okay. And a reversible process has the maximum efficiency. Okay. And rapidly occurring processes cannot be reversible. A reversible process should be a quasi-static or very slow process. But the important thing to know is that all quasi-static processes are not reversible. Okay. Factors like friction, unrestrained expansion, heat transfer through a finite temperature difference change, mixing of two different substances and chemical reactions or combustion make the process irreversible. And slowly occurring processes, heat transfer through negligible temperature difference, and fully reset processes may be reversible. Okay. Like these kind of these processes that like heat transfer through a finite temperature difference, unrestrained expansion, chemical reactions can also be done in a very slow manner. Okay, I'm not saying about chemical reactions. Say for unrestrained expansion or systems having frictional losses. Okay, let us take this one. This would be more understandable. Okay, so sir, imagine there is a piston cylinder arrangement and the piston cylinder has some friction, and even if we do the expansion or compression in very slow manner or very slow manner or almost a quasi-static manner, then also the system will not be reversible because of the reversibility is generated because of friction. Now if we consider same thing where there are no frictional losses and where there are no frictional losses and then we do it in a very slow manner, that process can be reversible. Okay, so this is the distinguishing fact between a reversible and a quasi-static process, that all quasi-static processes are not reversible, but all reversible processes are quasi-static. Okay, so again there are internal and external reversibilities. I don't think I need to go through it. So the important thing is reversible thermodynamic cycle. Okay, let us discuss about it. So most of the problems that we have in our hand will be based upon these formulas. So I emphasize that you uh, keep more attention to this part. Okay, so this part I guess was not discussed in the lectures, so if you have any doubt you can ask. But I'm just letting you know about it because there are some problems in assignments that are based on this topic. Okay, so I think eventually Professor Anand will discuss it in the next lectures, but just so that you will be able to solve the problems that we have in our hand in today's session as well as an assignment. I am letting you know about it. Okay, so for a reversible thermodynamic cycle we have ratio of the higher ratio of the heat transfer at higher temperature to ratio of heat transfer at a lower temperature. This is basically Q1 by Q2 as being equal to T1 by T2. Which book are you referring? So yeah, thank you. I am referring the book by P.K. Nag. It's a very let me write the title. Okay, so it is Engineering Thermodynamics by P.K. Nag. It is one of the reference books mentioned by Professor Anand. So there are, as an this book is again, as I must say, is being designed from a mechanical engineering perspective. Okay, since I myself is I'm a mechanical engineer, and the course that is being provided by Professor Anand is itself from a mechanical. How is Sontag? I'm extremely sorry. I don't know. I do not know about that book, but it's fine. Okay. Uh, other book was by, if I'm not wrong, by Turns. Yes, Turns. The first book. Let me just go through. Yes, Turns. Yeah. It's also a good book. It is I guess the first reference book given by Professor Anand. It's also extremely good, but for my sessions I prefer Pikena because I studied from it during my undergraduate. Excellent. Sengen balls are excellent, and in fact I suggest that this from the perspective of understanding or solving problems, basic problems, I think PKNAG is good because it will let you understand how the problems are solved in a simpler manner, like basically in understanding, taking data from the question and solving it. So in that perspective PKNAG is very good, but Sengen and Bowles I will suggest is the best book from the perspective of understanding the concepts, because Sengen and Bowles like explain the concept very nicely, like in-depth explanation of the concepts, in-depth explanation of the concepts in the questions, like how the terminologies used in the questions or the uh, values of the variables used in the questions comes into picture, they give proper explanation to these values in Sengel and Bose. So I think these are very good books. Okay, thank you so much, sir. Thank you. It's fine. Okay then. So yes, for a reversible thermodynamic cycle, we have that the ratio of heat interaction at a higher temperature to the ratio of heat interaction at a lower temperature. This is basically Q1 by Q2 is actually equal to T1 by T2. It is the temperature of thermal reservoir at higher temperature to the temperature of the thermal reservoir at the lower temperature. And now, so like this, I think for right now you can take it for just as something that I'm mentioning from my side, but there is a detailed derivation regarding this in the all the textbooks, say by Sengen and Bowles, by Turns or Pikenak. So all the textbooks give a detailed explanation how this engineering, automation, and robotics. It's fine. Like any book is completely fine. And moreover, this book, this course is introductory course to thermodynamics. Like in the we are teaching thermodynamics in the introductory level, so it's completely fine. Okay, you can use any book, whichever you have in our hand. And moreover, textbooks by Sengen and Bowles and I guess Pikenak as well are available in the PDF form. You need to search it for a bit, but I think it can be found. So it's completely fine. So I will suggest that if you are uh, starting or trying to solve problems or understand the course, the concept of solving problems, then I will suggest you can use Pikenak because problems are in a much more simplified manner, and moreover he's an Indian author. So for us, like for the competitive exams that we have in our hands, such as GATE, ESC, those things, Pikenak would be the best book because the problems are set up in a way that are being where the similar questions are asked in the competitive exams. But say if you're going to go on becoming a faculty in the later on or going to teach thermodynamics to someone, I'll suggest that you take the books by Sengen and Bowles or Stephen and Turns, where the concepts are very extensively explained. Okay, so it's important. So that's the distinguishing factor that I want to suggest. Otherwise, the book this thermodynamics fluid engineering book is also good, completely fine for an introductory course. But I'm just saying the aspects that the different books cover. Okay. Okay then. Just 1 minute. Just drink some water. Just 1 second. Okay. Then, yeah, the derivation of this is given in all the textbooks. Okay. How this is obtained, you can look into it. But right now I'm discussing it just briefly because I need to basically now apply it to solve the problems that we have in our hand. Okay. So now we find that efficiency of a reversible heat engine. So this term will basically mean that all the processes in the heat engine, the expansion, the compression, the heat interactions, all these processes occur in a reversible manner. Okay. When basically the efficiency of these reversible heat engines will be the highest possible efficiency for a heat engine. So the efficiency of a reversible heat engine in which heat is received solely at T1, basically that the heat interactions with the in the higher temperature as well as the lower temperature occurs in a uniform temperature. Okay, the temperature of the thermal energy reservoir does not change because of the transfer of heat from the reservoir to the system. Okay, that's why it is known as thermal energy reservoir. It has a lots and lots of energy, and some portion of energy is used to operate the engine, and the transfer of that heat from the reservoir to the system does not really change the temperature of the reservoir, and that's why it is a good approximation to take that the temperature of the reservoir remains constant. Okay, so the eta reversible or eta max, that is maximum possible efficiency for heat engine, is given by 1 minus Q2 by Q1 reversible, where since we know Q2 by Q1 is T2 by T1, so you can write 1 minus T2 by T1. So eta reversible is 1 minus T2 by T1, or in other words 1 minus TL by TH, where T2 is the temperature of the thermal reservoir at lower temperature or the sink, and T1 is the temperature of the thermal reservoir at higher temperature or the source. Okay, so TL by TH, or you can write also in this form, eta reversible is TH minus TL by TH. Okay. Then similarly, COP for reversible refrigerator, again refrigerator having highest possible COP is a reversible refrigerator, having all the processes occurring in a reversible manner. So the COP reversible refrigerator for reversible refrigerator would be T2 by T1 minus T2, because see, it's simple. Like initially we had COPR as Q2 by sorry, let me show you how I derived it. So COPR, if I recall, was Q2 by Q1 minus Q2. Okay, now if I take Q2 in the denominator, I will have 1 minus Q2 by, sorry, Q1 by Q2 minus Q1. Since we know Q1 by Q2 is T1 by T2 for a reversible process, a reversible refrigerator, so I will have this as T2 by T1 minus T2. Numerator must be yes. I will let you know about it. Thank you for mentioning that. Okay, thank you so much. So this is T1 by T2. Similarly, for a heat pump, it will be T1 by T1 minus T2. Yes, and as Anil rightly mentioned, all these temperatures, okay, in the case of say heat engines, or even in the case of refrigerators and heat pumps, all these temperatures must be taken in the absolute scale. And by absolute scale, I will mean that the temperature should be at Kelvin. Okay, so in order to trick you, the questions in the questions, the temperature might be given in Celsius, degrees Celsius, but in order for you to understand it properly, just for you to recall all these temperatures that you deal while finding the efficiency or COP, you need to take those temperatures at the absolute scale. Okay, because as Anil rightly mentioned about numerator, why? Because in the case of denominator, since it's a temperature difference, even if you take it at Celsius or Kelvin, it doesn't matter, difference will remain constant, right? Because Celsius, Kelvin is basically 273 plus temperature degrees Celsius, so even if you take the difference in Celsius, it will remain the same. But numerator will make the difference, because if you take it as Celsius, this will go very down, right? It will be very low, say 30 degrees Celsius by the temperature difference will give you some value, but and if you want take it in Kelvin, it will be basically 303 Kelvin by some temperature difference, which will again make it very high. Okay, so you need to recall that all these temperatures must be taken at the absolute scale, okay, in the Kelvin scale. I hope it is clear. So I think discussion part is up to here, so now we can directly go on to solve the questions that we have in our hand. Okay, so these are the questions that we have for today. So first question is, if a heat engine attains 100% efficiency, it violates the second law of thermodynamics. True or false? True. Yes, exactly. Because we saw that only way possible to achieve a 100% efficiency. Thank you so much, both of you. To both of you, it's only possible when we have PMM2, right? And only then we can have 100% efficiency, and PMM2 itself is imaginary device. So this is true. Okay, so a heat engine can never attain 100% efficiency, even in an ideal case. Okay, it's very important to know, even in an ideal case. Yes, so next question is, a reverse heat engine is operating between a source and a sink. The work done on the engine is 72 kilowatt, and the heat transfer to the engine from the low temperature region is 222 kilowatt. First, you need to find a coefficient of performance for a reverse heat engine when it operates as a refrigerator. So you need to find COPR, then COPHP. Okay, then I guess it's very simple actually. Formula is COPR, let us say it will be QL by QH minus QL, or QL by W net. Okay, so just use this formula and then tell me the answer. No need to bother about temperature, because the heat interaction itself are given, so you can let me know. Okay, let me give you 4 minutes to find the answer, then we can discuss about it. Okay. 3. Okay. What about COP of H pump, the heat pump? 3 star 1 or 3 plus 1? Yes, exactly. Thank you. So the answers are correct. So you just basically need to do 2, 2, 2 QL, because QL is given, this is equal to QL and this is equal to W by 72. So you will find it out as say 222, sorry, 222 divided by 72 will turn out to be 3.0833. So I will suggest that you keep the decimal points as well in picture, because I guess in the assignments they ask up to 2 or 3 decimal places, so that need to be kept in mind. Similarly for heat pump, again you can use different techniques to find this. Other simple one is to do 1 plus COPR, but other way could be this one again. So since you already know QL by QH, so you know QL, right? QL is 72 and QH minus QL is W net, that is, sorry, I'm extremely sorry, QL is 222 and QH minus QL is 72. And since you know both of them, you can easily find QH, that would be 72 plus 222, that would be 492, right? 294. Now you can easily find that COPHP, it would be basically be 294 by 72, 294 by 72, this will give you 4.0833 exactly. Sorry, yes, thank you. So these are it. So you see, answers are, both the answers are correct. If you know COPR, you can use this formula, otherwise you can use this as well. Okay, same thing. Let us go to the next question. I hope this is clear. Now let us go to the next question. According to Kelvin Planck's statement of the second law of thermodynamics, so you need to tell me which of the following statements explains the second law of thermodynamics from the Kelvin Planck's approach. So what is the Kelvin Planck statement for the second law of thermodynamics? A. So it tells that it is possible to construct an engine working in a cyclic process whose sole purpose is to convert heat energy into work while dealing with only one heat reservoir. Is it? It mentions that it is possible. It is possible to construct a heat engine working in a cyclic process whose sole purpose is to convert heat energy into work while dealing with only one heat reservoir. So A is not correct. So I suggest you look in the options carefully. It seems A is not correct because it is mentioning that you can the system can generate work while interacting with only one heat reservoir. Okay. So the correct option, you can look into the statements. One of the statements is correct. It's the interplay between the words. Read the statements carefully. So the correct answer would be option C. If you read it again, you'll understand. So option A and C are just the inverse of each other, right? One says it is possible, one says it is impossible, right? So option C says that it is impossible. It is sorry. It is impossible to construct a device that will operate in a cycle and produce no effect other than raising of a weight in the exchange of a heat with a single reservoir. So produce no effect other than raising of a weight basically implies there would be a work interaction in the exchange of heat with a single reservoir. So and it's impossible. So the correct option would be option C. Is it clear? It was just a interplay of words, but option C would be correct. Okay. So let us go to the next question. These are again numericals, so I hope you have calculators in hand. So a cyclic heat engine operates between a source temperature of 800 degrees Celsius and a sink temperature of 30 degrees Celsius. So you are given TH as 800 degrees Celsius and TL as 30 degrees Celsius. What is the least rate of heat rejection per kilowatt of net output of the heat engine? So we need to find Q heat rejection L per kilowatt net output of the engine. So you are even told W net is 1 kilowatt. So this is a key term, right? Least rate of heat rejection per kilowatt net output of heat engine. Okay, so I think all these things are given to you. You need to find out the QL. Okay, and least rate. So you think, when is it possible to have least rate of heat rejection? In which kind of heat engines there will be least rate of heat rejection? Eta is 1 minus QL by QH. So I will give you say 5 minutes to solve the problem. It's not that difficult. It's just about finding efficiency in the net heat rejection, and then you can find. It's quite simple. Try it out once, then I'll show you the solution as well. $1.39. Yes, it's correct. You need to find QL. What would be QL? Exactly. So it's correct. Okay, so Deve, do you need some time to solve the question, or we can look into the solution? Okay, let me wait for 1 more minute for him to as well try. I'm sorry if I'm. Meanwhile, Anil can try the next question as well. I'll read it out once I show the solution for question number 4, just for other viewers as well who will be attending the video, see the recorded video. You can try question number 5 as well, but I will first tell the answer to question number 4 and like how it is being solved, then go to question number 5. Okay, so I'm sorry, let us go to the solution once. So go back. Yes, here. So temperature TH was 800 degrees Celsius and TL was 30 degrees Celsius. So the key thing here is now to convert these temperatures first to absolute scale. So the higher temperature, or the temperature of the source is at 1073 Kelvin, and the temperature at the sink is at 303 Kelvin. Just plus add 273 to both, you will get the value at the Kelvin, temperature at Kelvin. So the key thing to know is that the heat reaction will be minimum for a reversible heat engine. Okay, Q2 will be minimum for a reversible heat engine. So that was a crucial part for this problem. So you need to find the efficiency considering that this heat engine is a reversible heat engine. So in the case of reversible heat engine, eta reversible would be 1 minus TL by TH or T2 by T1. So just substitute the value of T2 and T1, you will get that in the absolute temperature scale, you will get that eta reversible is 1 minus 303 by 1073, or eta reversible is 0.718. Now we also know that eta reversible or eta is W net by Q1, and net work done by the net heat input. So net work interaction is 1 because it's asked to find the net heat reaction per kilowatt output of work. Okay, so net work output is 1 and divided by Q1. So we already know eta reversible. So eta reversible is 0.718. So we write it as 0.718 equal to 1 minus 1 divided by Q1. So Q1 would be 1 by 0.718. This is what exactly I have done here. So we get Q1 or QH as 1.392 kilowatt. And then we need to find Q2 or QL. So we know that Q1 minus Q2 is the net work interaction, or Q1 minus Q2 is equal to 1. So from here we can get Q2 as Q1 minus 1, so 1.392 minus 1, so Q2 or QL as 0.392 kilowatt. Okay, so I hope this is clear. It's quite simple problem. Okay, so let's go to the next question. Question number 5. A domestic freezer, freezer, these are key terms. Freezer maintains a temperature of minus 15 degrees Celsius. Okay, so from here you got, TL. The ambient temperature is at 30 degrees Celsius, it is TH. If the heat leaks into the freezer at a continuous rate of 1.75 kilojoule per second, this is QL, what is the least power necessary required to pump this heat out continuously? So you need to find the least power required, or you need to find W net, network input into the refrigerator. Okay, so again I think for this you need to go to the formula for the COP, that is QL by QH minus QL, or in this sense it will be QL by W net. So you need to find we need to find the COP, then compare it with this equation to get W net, because you already know QL, this 1.75 kilowatt. So you need to find W net. Okay, again quite simple. The key terminology is the least power necessary. So in which case you will require the least power, or in which kind of refrigerator you will require the least power. Okay, something similar to what we discussed in the previous question. Least heat reaction is in the case of a reversible heat engine. So in which case you will require least power for a refrigerator. Which kind of refrigerator will have a least power requirement? Okay, so that's the key. You can try it out. Let me wait for 4 more minutes and then we can proceed. Again, take the temperatures at the absolute scale, it is at Kelvin, to find out COP or efficiency. Sir, we find this question, we need to find the W net. Yes, yes, exactly. Ten point zero three. Okay, let me check. Hmm. No, it's not. It's not correct. You can kindly check the units. Kindly check the temperature scale. Have you taken it correctly? It might be the case. Otherwise, I think it's correct only. So, but the values are wrong. It's not 10.03. Okay, just check it once again. Just try it out. That's fine. I will eventually let you know the answer. So let me give one more hint. So the least power requirement would be in the case of a reversible refrigerator, right? So COP, sorry, COPR reversible, you can find out, right? Because you are already given the temperatures uh, at the of the source in the sink, right? So we'll have, it would be basically be TL by TH minus TL. Find this one and then equate it to QL by W net. Okay, say its value is say lambda, then you can easily find W net as Q by lambda. 58.3, no, sorry, it's not correct. Okay, then I guess we can 5.73. Yes, yeah, maybe I have to check, but yes, it is correct. 5.73. Let me just calculate it right away. So TL would be uh, and 45. So yes, 5.73. Correct. COP is 5.73. Now we just need to find W net. QL is also given. Yes, exactly. That's correct. 0.3054 is correct. So if you go to the solution, this is again, it was quite simple. You need to find TL and TH. Okay. Why? Because you need to find it in the Kelvin scale. Okay. So TL is 258 Kelvin and TH is 303 Kelvin. So the minimum power requirement is in the case of a reversible refrigerator, or COPR becomes COPR reversible. So the COPR would be TL by TH minus TL, or 258 by 303 minus 258. That comes out to be 5.7333. Right. Now COPR would be QL by W net. W net will be 1.75 because QL is already given, is equal to 1.75. So it will be 1.75 by 5.7333, or W net is 0.305 kilojoule per second or kilowatt. Okay. Now let us go to the next question. A Carnot yeah, required effect by net work done. Yes, exactly. Thank you. The required effect in this case was the heat absorbed from the stored food items. So basically, heat interacts at a lower temperature is the required effect in the case of a refrigerator. Okay. So a Carnot engine absorbs 200 joules. Carnot engine, again a key term. Carnot engine absorbs 200 joule of heat from a reservoir at a temperature of a normal boiling point of water. So the reservoir temperature is given and rejects heat to reservoir at the temperature of triple point of water. So these are the key terms. You need to know the triple point temperature and the boiling point temperature. Find the heat rejected, the work done by the engine, and the thermal efficiency. and the thermal efficiency. So here it is Carnot engine, so it is again simple that it is a reversible cycle. Carnot engine is a reversible cycle, reversible heat engine. Okay, absorbs heat from the reservoir. So basically it tells you that QH is 200 joules. Okay, and TH you need to tell me normal boiling point of water. TL is triple point of water. You can find it out, already given. And you need to find the heat rejected, that is QL. You need to find out work done by the engine, W net. Once you find QL, W net can be easily found. It is QH minus QL, and the thermal efficiency eta. So that will basically be 1 minus TH by TL. Why? Because they have already mentioned it is Carnot engine, and Carnot engine is a reversible heat engine. So eta would be 1 minus TH by TL. So again, it's quite simple. Okay, just I'll give you say four more minutes. Try it out and let me know. Quite simple again. What's the boiling point of water? Convert that into Kelvin scale. What is the triple point of water? Again, convert the temperature. Key thing is temperature of the triple point, not the state of the triple point. So pressure may be different in the case of triple point, but the key is the temperature at the triple point. So temperature at triple point is constant. So you need to know that. Exactly. Then the boiling point. So repeat question number 6. Okay. So it is told that a Carnot engine absorbs 200 joule of heat from a reservoir at a temperature of the normal boiling point of water. So the higher temperature, that is TH, is the boiling point of water. Okay, so you need to know that. Okay, similarly, and rejects the heat to the reservoir at the temperature of triple point of water. So TL is also given, that is triple point of water. You need to know that. And it is mentioned that the QH, or the heat absorbed at the higher temperature, is 200 joules. Okay, so you need to find the heat rejected, which is QL, the net work interaction, that is W net, that I already told. It would be QH minus QL, since it is operating in a cycle, and the thermal efficiency eta. And eta can be given as 1 minus TH by TL, because it is a Carnot engine, which is a reversible heat engine. Okay, so I hope the question is clear. Okay, so Anil has already mentioned that, yes, exactly, both are correct. So Anil has already mentioned that the triple point is 273.16 Kelvin, and the boiling point is 373 Kelvin. Okay, so since you already know TH and TL now, you can find the efficiency, thermal efficiency, right? And once you find the thermal efficiency, then you can easily find the net work done, right? from that you can find QL, there is the net heat rejected, and everything is found out. Okay. So let me try it out. So eta would be 1 minus 300, sorry, 273.16 by 373.15. So just taking exactly, we can keep 370 as well. So you get some value, say alpha, right? Now W net by QH is alpha, right? So from here we can easily find W net. W net would be alpha into QH, right? Now you again know W net is QH minus QL, so QL would be QH minus W net, or QH minus alpha QH. Okay, I'm not writing the values because you need to find it out, so I'm just writing in terms of some variables. So this is the way you need to find. So okay, 26.79%, correct. Efficiency is 26.79%. So one thing is found out, that is thermal efficiency. If I go back, it is found out. Then work done by the engine can be found out by this manner, and heat rejected QL can be found out this manner. Okay, everything can be found out. QH is already given, it is 200 joules. So you need to find W net. So W net will be 0.2679 into QH, there is 200. So let me try it out. 0.2679 into 200. So it will come around. Okay, I'm sorry. Sorry, like sorry, the screen was, sorry from my side for the issue. Okay, let's share the screen again. Okay, sure, I will solve it. Okay, sorry from my end, the screen was connection was lost. Okay, so Deve asked me to solve the question. Let us try it again. I think Anil will easily solve, since we already found the efficiency, every other terminals will easily found. So let us try the solution. Okay, so yes, this is question number 6. So Q1 is 200 joules, okay, and temperature, and it receives heat at higher temperature. This TH is 373.15. This is the boiling point of water, normal boiling point of water. Okay, it is pressure is at atmospheric pressure. Similarly, T2, there is a lower temperature of heat interaction is 273.16. It is a triple point of water. Okay. Now, eta efficiency can be easily found out as 1 minus T2 by T1, or TL by TH. So 1 minus 273.16 by 373.15, you get eta as 0.268. Okay. Now we also know that eta is W net by Q1, right? So W net can be found out by eta into Q1, that will be equal to 0.268 into 200, or W net is 56.3 joules. Okay, so right, so now we need to find out QL, right? Now we also know that W net is QH minus QL, or 53.6 is equal to 200 minus QL, or QL is equal to 200 minus 53.6, which will give you 146.4 joules. Okay, so is it clear? Yes, exactly. Okay, forgive me the decimal places, so it's fine. Okay, I hope it is clear. Deve, is it clear? Okay, you have question? Yeah, you can unmute. Yeah, you can ask. What's the question? What's the doubt here? Oh, I'm sorry again. It's got disconnected. Sorry for the issue from my end. It's got disconnected again. Okay, sorry. Yes, Deve, you have any doubt? Please ask. Is it clear? Can we move forward, or should I repeat it again? Okay, fine. Like, if you need doubt, you can ask or even type it on the chat box. Okay, let us move forward to the next question. Okay, thank you. So let's go to the next question. So this is the final question for today's class. Let me zoom out a bit more. Okay. So it's a very extensive question. It's a bit more complicated than other two questions that we had discussed today. So let us try it out. Okay. A reversible heat engine E1 operates between 900 Kelvin and a temperature T2. Okay. It is, the diagram is given here. It operates between 900 Kelvin and temperature T2. Okay, where T2 is less than 900 Kelvin. Okay, T2 is less than 900 Kelvin. Okay, and another reversible heat engine E2 operates between T2 and 400 Kelvin. Okay, so T2 is greater than 400 Kelvin. The heat received by E2 is equal to heat rejected by E1. So this is a very crucial statement. So heat rejected by E1, this QE1 is equal to heat received by E2 is equal to heat rejected by E1. So heat rejected by E1 is used as an input for the second heat engine E2. Okay, so QE1 2 would be equal to QE2 1. Okay, it's a very important statement in the question. First is, if both engines have the same work output, then what is the value of T2? If, so basically they're asking if they're asking if WE1 equal to WE2, what is the value of T2? Secondly, they are asking if both heat engines have the same efficiency, what is the value of T2? So if eta E1 is equal to eta E2, what is the value of T2? Okay, so this is the question, and I hope the question is clear. So basically, two heat engines are operating in tandem. So the heat rejected from E1 is used as an input for heat input for the second heat engine E2. Both are emitting work WE1 and WE2 respectively, and they are operating at a temperature range of 900 to T2 for the first heat engine and T2 to 400 for the second heat engine. So it basically means 400 Kelvin. Sorry. So T2 lies between 900 and 400 Kelvin. Okay, so you need to find T2 for the first case when WE1 is equal to WE2. Okay, is the first case. Secondly, if both engines have same efficiency, basically eta E1 is equal to eta E2. Okay, so let us do part wise. Again, for part 1, let me give you 5 minutes. Try out the part 1. Then after 5 minutes, I will show you the solution. Secondly, then again we'll discuss the part 2 as well, and then I'll show you the solution. I hope it is fine. You can try it out now. Okay, I'll give you 5 minutes for the part 1. I hope the question is clear. Okay, if you have any doubt in the question, you can ask me again. Okay. And the key term is again reversible heat engine. Okay, reversible heat engine. So these formulas you can use. So eta would be 1 minus TL by TH, or you can also use QL by QH is equal to TL by TH. So these are the two formulas that you can use in the case of reversible heat engine. So these two formulas will come in handy. Okay, so try it out. It's a bit more challenging than the questions that we solved till now. Less than Y for T2. No. T2 is less than 900 Kelvin. See, T2 is less than 900 Kelvin. I've shown here as well. It has to be lower than 900 Kelvin, then only the heat interaction can occur, right? Spontaneous heat interaction. I hope it is clear. Just consider it as two heat engines, right? Two heat engines operating in a series. So the heat source for the heat engine 1 is at 900 Kelvin, and it rejects heat at a temperature of T2. Now this heat sink for the first heat engine is acting as a source for the second heat engine, which operates between a temperature range of T2 Kelvin to 400 Kelvin. Okay, so T2 should be greater than 400 Kelvin. And both these engines have respective heat interactions and work output given by WE1 and WE2 respectively. So you need to find the temperature value for WE1 equal to WE2, where the work output from both the engines are same. Second, you need to find the efficiencies. You need to find the temperature T2 for the case where the efficiency of both the heat engines are same. Okay, so let me try give you some hints. Maybe it will be helpful. So let us try Q1 by 1 minus Q1 2. Okay, so let me have to check it. Okay, yes, exactly. So since we have WE1 equal to WE2, right? Exactly, you have correctly mentioned it. So what Anil is trying to mention is that, so for heat engine 1 we will have QE1 E1 comma 1 minus Q E2 comma 1 would be equal to Q E2 comma 1 minus Q E2 comma 2. Sorry, I have misplaced the suffix. So it's not suffix, this term. So I'm again sorry, this would be 2. Okay, so yes, exactly. So here, since we know that Q E1 2 is equal to Q E2 1, because it is mentioned that the heat rejected from E1 is used as a heat input for the second heat engine. So this is this holds valid. So just divide both the equations, both the sides by QE12. So we will have QE11 by QE12 minus 1 equal to Q. I hope I can scroll up a bit. This would be 1 minus QE22 by QE21. Okay. So as Anil rightly mentioned now, since again these are, yeah, exactly, the answer is correct. Okay, so since these are reversible heat engines, so we'll have, if we take this as T1 and this as T3, say, to simplify it, you will have T1 by T2 minus 1 equal to 1 minus T3 by T2. Okay, so we'll have T1 plus T3 by T2 equal to 2. Okay, just simplifying this equation, then we'll finally get T2 as T1 plus T3 by 2, or 900 plus 400 by 2, or 650 Kelvin. Okay, so just for the clarification, thank you so much, Anil. Just for the clarification, let me show you the solution for now, as well as for the viewers, other viewers as well who will watch the video. So this is basically the problem that we have in our hand. Okay, so I have taken 900 Kelvin as T1 and 400 Kelvin as T3 for simplification. Okay, for simplification purpose. Now all other terms are exactly same as the diagram that was shown. QE1 is the heat input to the heat engine 1, QE12 is the heat rejected from the heat engine 1, and WE1 is the work output from the heat engine 1. Okay, similarly QE21 is the heat input to the heat engine 2, and QE22 is the heat rejected from the heat engine 2, and WE2 is the net work output from the second heat engine E2. And it is told that QE12 is equal to QE21. It's not that complicated. Basically these two are equal. Okay, so the first case is if both the heat engines have the same work output, basically, then WE1 equal to WE2. Then we know that for cyclic process, W net work output is net work output is equal to net heat interactions, or WE1 would be equal to QE11 minus QE12, right? So that is what I have exactly written here. So W1 would be QE11 minus QE12, and W2 is again QE21 minus QE22. So it is QE21 minus QE22. Okay, so since we already know that this is the crucial step. Okay, since we know that QE12 is equal to QE21, okay, this is already mentioned in the question as well. Okay, then we can divide this equation by this and this equation by this. Okay, so if we take it in a denominator, we'll have QE11 by QE12 minus 1, that will equal to 1 minus QE22 by QE21. Okay, and since we know this is a reversible heat engine as mentioned in the question, then QE11 by QE12 would be equal to the temperature ratios, right? So QE11 would be T1, QE22 by T2, so QE11 by QE12 would be T1 by T2 minus 1, that would be equal to 1 minus QE22 by QE21, that would be equal to T3 by T2. So this would be equal to T1 by T2, and this would be equal to T3 by T2. That's what I have written here. Okay, so from this equation now we can write it as, take this one here and this one in this side. So we will have T1 plus T3 by T2, since denominator is same for both the cases, would be equal to 2. Okay, or just take 2 in the denominator now. So we'll have T2 as T1 plus T3 by 2, that would equal 900 plus 400 by 2, that will equal to 650 Kelvin. Okay, In this case, it is the arithmetic mean. Yeah, it is arithmetic mean in this case. For same work output, the temperature for the T2, the unknown temperature is the arithmetic mean. So now second, in the second case, you need to find out if the both hit in this have same efficiency, what is the value of T2? So eta E1 equal to eta E2. So it will basically be, let me give you a simple hint. I know you already know, but let me give you a hint. It would be 1 minus T2 by T1, that would be equal to 1 minus T3 by T2. Just solve this equation and then find T2, because you already know T1 and T3, right? Just let me know the final solution. Same efficiency. For same efficiency, this will be the case, right? Okay, I'm again sorry. This battery saving mode is on, so the screen switches off itself all the time. Okay, sorry for this issue from my end. Extremely sorry. Have you tried it out? 1 minus T2 by T1 equal to 1 minus T3 by T2. You need to find expression for T2. Quite simple again, not that difficult. Okay, so it would basically be, now if we continue with this equation, you will get 1 will get cancelled out, so you will get T2 by T1 would be equal to T3 by T2, or T2 square equal to T1 and T3, or T2 would be equal to square root of T1 and T3. Okay, yes, it is geometric mean. Yes, it's 600. Okay, regarding the calculator, I am extremely sorry, I don't know about the specifications. uh, I'll talk, I'll discuss, I will ask about it to the NPTEL management, whether this is allowed or not, and then let you know. Okay, in the next class, if you join, I will let you know. Even I will, if you don't even join, I will let you know I will announce it in the lectures. Okay, before the lecture starts, before the problem solving session starts, I will let you know whether you can use calculators or not in the exams. Okay, sorry for the lack of knowledge from my side. Okay, okay then, that's all for today from my end. Yes, exactly. Exam dates, yeah, exactly. So that's all for today from my end, and thank you so much for attending the online. Yeah, I guess Anil knows much more better than me, so please thank you for the information. But still, yeah, on screen, yes, I will still confirm with the NPTEL management and then let you know in the next session. Thank you then. That's all for today from my side. No. This won't be allowed, I guess. You cannot change in the tab. I'm NPTEL star. Okay. Okay. Thank you so much then. Uh, Thank you for attending the session, and okay, then I will ending the class now. So, thank you. Thank you so much. Thank you, Anil. Thank you, Deve.